Hello dear students. So this is a series where we will be discussing mathematics behind artificial intelligence. So this is video 1 in that series. So I should write video 1 because we are going to make so many videos, because there is so much of mathematics which is used for artificial intelligence. So we'll be, there are so many things. You may work without it also. If you are learning artificial intelligence, then you can just remember, okay, so this is the formula we are using. But because it is always important that you know what exactly you are doing with mathematics, then only you can improve, like you can improve your algorithms, or you can actually, play with your algorithms if you actually know what is the mathematics behind it, right? So it's good that if you know why a certain thing is used the way it is used in artificial intelligence, why not something else? For example, the first question we are going to answer in this video, or first thing we are going to see, that how exactly mathematics is being used for artificial intelligence. So you must be knowing that linear regression is one of the most important part of machine learning, and then for artificial intelligence. So what is linear regression? Linear regression is basically, if you have, suppose you have some data. For example, I have data like time, and then the temperature at certain, like at different times. I have a data for temperature. For example, at 10 a.m. the temperature is, say, 5 degrees Celsius, right? And then at 12 a.m. the temperature is 6 degrees Celsius, and so on. So I have data, right? And somewhere where I don't have data, for example, between 10 and 12 at 11 a.m. I don't have data, but I want to predict what will be the temperature, right? So this is a very important problem in machine learning. For example, if you have, depending on the number of bedrooms, the house price is there. So you have number of bedrooms, okay, and then you have the price of the house. So you have these two things. Suppose 2 bedroom, then you have the price as 5, say whatever is the unit, right? 5 units, it may be 5 crores. And then for 3 bedrooms, it's 7 crores, and so on, right? So now suppose then I have 5 bedrooms, say it's 9 crores, and in between I want to predict what about 4 bedroom house, right? So things like this, that is your regression means you want to interpolate the data. You should have the in between information where you don't have the exact information. So that is what we are doing in machine learning all the time. We are doing this type of things, right? So you have data, but you don't have data everywhere. So you try to fit where you don't have data, like you don't know the value of your output, you try to predict that output, right? So that is called regression. So here I'm just taking example of that. There is only one feature, this is called feature, but we can have more than one feature, right? So we can have, for example, if you work on the problem of housing price, you can have number of bedrooms, you can have location, you can have area of the house, then you can have like which school is near to your house. So many factors are there which can play into the price of the house, right? So instead of just having one feature, like here we had only one feature, you can have multiple features. So in linear regression, what we do exactly, so we have data. So you have data, right? So I assume that data, the word I'm using features, right? If you are a person from machine learning or artificial intelligence, you must be knowing this already. If not, it's not a big deal. So what is feature? Feature is basically, suppose I told you that number of bedrooms, the size of the house, location, so whatever are your independent variables, right? So suppose my independent variables are n features, right? So I'm assuming that n features. So it means that data will be like this. Data, the first entry in the data will be, I have x1, and the corresponding I have n features. So I have x11, x12, x1 3 and so on x1 n. So these are my independent variable, and corresponding I have one label. Like I know this data, like if these are the values of the input, this is my output, right? And then for x2 1, x2 2, x2 3 and so on x2 n. So these are the second level features, and this is my corresponding label. It is called label. Okay, this is basically, if you are a person from mathematics background, so these are your independent variables, and then you have, this is your dependent variable, right? And in artificial intelligence or machine learning terms, we call it as features, we call them as features, and we call them as labels, right? And then you have at, like suppose I have m data, right? So we say that we have m examples. So we have mth data, and the corresponding features are xm1, 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 m2, xm3 and so on xmn, and the label is ym. Okay, so this is what we have as our data. And what you are trying to do is, you are trying to predict a function. You try to predict a function. And one more thing before that, I'll denote this whole set as x1 and this whole set as x2 as a vector, right? This as xm, and basically I'm assuming x1 to be x11, x12 and so on x1m, and then n, sorry, and then x2 will be x21, x22, and then you have x2n and so on. Similarly, your xm will be xm1, xm2 and so on xmn. So what we are saying here, that you are given x1 data. So you in your mind should be clear that it is a vector. The corresponding output is y1. Then you have x2 data, and the corresponding output is y2 and so on. Then you have xm data, and the corresponding output is ym, right? So what is this? This is that you have only corresponding to these features you collected the data. For example, suppose you are a property dealer, so you go to a particular locality and you collect all the data. So what you have, you know that, okay, corresponding to these features, these will be my house prices, right? Now I would like to know, because I cannot go to infinite number of houses. So there are almost infinite number of houses, so I am unable to go everywhere. So I would like to use artificial intelligence for any kind of prediction in between, right? So what we are trying to do, you try to fit a mathematical function. You say, okay, if I somehow know that this h of xj, right? So this is a function. This is a function. If I know that my yj is h of xj, then I am very happy. So in artificial intelligence, we call it as hypothesis. We call this function as hypothesis, right? Because this is what we are predicting, right? So this is our hypothesis, that this is the function which will work, right? Now because we cannot be so optimistic that we expect an equality sign, so we expect, okay, this may not be exactly equal, so this is approximately equal, right? So we are looking for a function which is such that given these data points, right? So we already have this data, so we have to work with this data. So we are looking for a function which at least works very good on these data sets, and then it works for our like predictions also, right? So this is what we are looking for. And in linear regression, what we do, we assume that this is equal to some number theta naught plus theta 1 xj1 plus theta 2 xj2 and so on theta n xjn. So this is what we do in linear regression. We assume the hypothesis function to be this, okay, this. So theta naught, theta 1, theta 2, theta n. These are the unknowns which you have to find out. We call them as parameters. Right, so these are the unknowns. So you will see that in books what they do, they introduce another feature xj naught as 1, so that they can write h of xj as theta naught xj naught plus theta 1 xj1 plus so on theta n xjn. Now I can write it as xj naught xj naught, or we can write the theta vector first. So I can write it as theta naught, theta 1, theta 2, theta n, and then you have this column vector here, xj naught, xj1, xjn. Sorry, xjn. So this is, I'll call it as theta transpose because I'm assuming my vectors to be column vectors, and this is my xj. Right? So we in linear regression, this is the hypothesis function. Okay, so you should remember. So you will see that we can go for like quadratic regression also. In that case, your function will be something else. But for linear regression, this is what our function is going to look like, right? So now your job is to find out theta. Your job is to find out theta. Right, in such a way that your hypothesis does a good job for the data which you already know. Right, so we say, okay, so what we can do is, so if we work with our hypothesis, so for the first feature set, the hypothesis prediction will be, so this is my example 1, example means my data set 1, it will be x1, right? So your feature was x1, so you have theta transpose x1. This is your prediction, but your exact prediction is, exact value is y1. So error will be theta transpose x1 minus y1. Okay, and then similarly for the second example you have x2. So your hypothesis prediction is theta transpose x2 and the exact value is y2. So your error is theta transpose x2 minus y2. And so on. For the third one, your hypothesis prediction is x transpose x3 and the exact value is y3. So the error is theta transpose x3 minus y3, and so on. And for the mth example, you have theta transpose xm, this is the value predicted by your hypothesis, and this is the exact value. So your error is theta transpose xm minus ym, right? So now obviously it should become in your mind, it should be in your mind that we would somehow try to minimize these errors. That should be our job, right? And in linear regression you will see that they will say, okay, go for this function 1 by 2 theta transpose xj minus yj square j from 1 to m and minimize it. Minimize this function. Then this is an optimization problem. Minimize this function and we call it as cost function. Okay, now okay, if you are just an obedient student, you'll say that okay, I'll obey whatever is in the book and I'll just minimize this function and everything will do very nicely, like you will get all your results very nicely. But the question is why we are taking square? Why not this error simply, right? If I ask you, so some of you may answer me like this, okay, if you just add these errors and try to minimize, then positive and negative quantities will be cancelled, and then because the positive and the negative quantities will be cancelled, so that means that we are not getting an exact picture of the error. So that's true, but then I'll say that okay, why not take modulus of each error, so your problem will be solved. Why you are only taking squares, right? So although squares are doing a good job, but we would still like to know the answer why we are choosing this square, right? Why not cube or raised to power 4 or something like that? So the answer lies in, the principle of maximum likelihood. Principle of maximum likelihood. So if I hope that you have already studied probability theory. If not, then I would recommend you, like I have a series on probability and statistics. You can go there and you can see that theory, like this that series, because probability and statistics is very important subject as far as artificial intelligence is concerned, right? So you should know your probability subject inside out if you really want to work on artificial intelligence. So we have principle of maximum likelihood. What is this principle? So this is very this is a principle which is we actually we can understand from a real life, right? So principle of maximum likelihood, as the name tells you, it says that suppose you have a model, right? You have some model and there are some unknown parameters in your model. For example, in this case, this is our model. This is what we are predicting. Xj is equal to theta transpose xj, right? So principle of maximum likelihood says that you have a model, then you have parameters. For example, thetas in our case. So these are unknown parameters. So this principle says you collect some data. Collect some data. We already have that data, right, with us. And then for each data point, suppose you collect 100 samples, right? For each data point, you find the corresponding probability. Find the corresponding probability. Okay, so for example, if you have 100 data points, so you will have 100 probability values. So you have 100 probability values. Now you take the product of all the probabilities. Right? So you have, suppose you have I from 1 to 100 PIs. Now you see what is happening. You started with a model and you got these 100 values from your model. And this is the probability of getting these 100 values. Now because you have already found these 100 values when you were actually sampling, so it means that your thetas, unknown parameters, should be such that this probability is maximized. Do you understand? Because this is what we have already got from our model. So you had a model, you had some unknown parameters, right? You don't know the values of the parameters. So what you are doing, you collect some sample. Suppose you collected 100 samples, and for each sample which you are getting, you find the corresponding probability, right? Now you multiply all those probabilities. These probabilities will be in terms your thetas, whatever your unknown parameters are there, and you make the product of all the probabilities. So this is called likelihood function. This is called likelihood function. Okay, now because you already got these numbers, so it means that your thetas should be such that this probability is maximized because you already got this sample, right? So that's the idea of maximum likelihood. So we'll try to apply this here, right? So what I will say, I'll say that, so lots of probability theory will be used. So don't worry if you don't know probability theory, then I will recommend that you first watch the probability theory videos, then you can come back, okay? But I'll tell each and everything. So what is our problem here? So we have this problem that yj is our data, like labels, okay? And then H transpose xj, this is our hypothesis. And this, because they are not equal, so this is error, right? So this is your error. So you should understand that this error term is going to be normally distributed. Now you should know what is a normal distribution. So most of the things which are happening around us, they are normally distributed. Most of the process which they produce numbers which are normally distributed. So normally distributed curve is something like this. So this is the probability distribution having a bell-shaped PDF, right? So this is the graph for normal distribution. So we have your errors, because you expect that positive and negative errors. So you expect that this is a normal distribution whose mean is 0 and variance is some sigma square. We don't know what that is, but that is a sigma square, right? So this is what we are expecting, right? So the graph of this function is 1 by square root of 2 pi sigma e raised to power minus epsilon j minus whatever is the mean. Mean here is 0 square upon 2 sigma square. So this is the PDF of epsilon j. PDF of epsilon j means probability. What is the probability of getting the value epsilon j, right? Okay. So now if this is the case, now if this is normally distributed, this is then yj is also normally distributed, but because this number you are subtracting, so yj is also normally distributed, whose mean is h transpose xj and whose theta transpose xj. This was theta transpose xj, whose mean is theta transpose xj and whose variance remains same, right? So you know, if you have some numbers, say 5, 7, 9, 11, and you subtract, and it has some mean. So you have some numbers, right, and it has some mean, say here. Now from each number you subtract 2. You shift each number to left. Then the mean will also be shifted by the same number. But the variance remains same. The outreach of the data, like variance means what is the width of the data, that will not change. So the same thing is happening here. Your epsilon j is normally distributed with mean 0 and variance sigma square. So this new variable yj is nothing but just you are adding theta transpose xj to epsilon j. So this will be having mean changed and variance remains the same, right? So it means that what will be the probability of yj? So PDF of yj will be 1 by square root of 2 pi sigma e raised to power minus 1 by 2. Now you will have yj minus theta transpose xj. Okay, xj is in the top, square sigma square, right? So now, because I want to find out my thetas, so I'll say, so my likelihood function will be that I'll multiply all these probabilities. So I have m examples, j from 1 to m, 1 by square root of 2 pi sigma e raised to power minus 1 by 2 yj minus theta transpose xj over sigma square, right? So this is my likelihood function. Now you have to maximize this, because we call it as L theta, and generally you'll see that we always take log because it makes the maximization problem easy. So we take logarithm. So this is log of L theta. We denote it with small l theta. We call it as log likelihood function. Log likelihood function. So in this case, you see what will this, because this is product, so you'll have sum. So we'll have sum j from 1 to m. Inside I have to take log. So it will be log of 1 by square root of 2 pi sigma e raised to power minus 1 by 2 yj minus theta transpose xj over sigma square. Now we know log of a times b is log a plus log b. So this will be j from 1 to m log of 1 by square root of 2 pi sigma plus log of e raised to power minus 1 by 2 yj minus theta transpose xj over sigma whole square. Now you know that this term will come here because we know that log of a raised to power m is m log a. So this term, because this is a constant, so this becomes m times log of 1 by square root of 2 pi sigma plus this will be summation j from 1 to m. This comes in the front minus 1 by 2 sigma square yj minus theta transpose xj whole square. So this is my L theta. You want to maximize it. So this is m log of 1 by square root of 2 pi sigma minus 1 by 2 sigma square j from 1 to m yj minus theta transpose xj square. Now you want to maximize it. You want to maximize it. Now because this is negative and this is a constant, this is constant, this is constant, everything is constant. So that is equivalent to minimize this quantity here. Sigma ij from 1 to m yj minus theta transpose xj square. 1 by 2 we take because it leads to some nice mathematical things later on. So you see, this is the cost function you are using in linear regression, right? If you look at the book, they'll just tell you that this is what you have to use. But you see how beautifully mathematics is telling you. The principle of maximum likelihood is telling you that this should be your cost function actually. And it is coming from the probability theory. So that's very accurate, right? Okay, now we know that why in linear regression we use this as our cost function. There are other reasons also, but this is now it's authentic, right? For example, sometimes you like something is very authentic, for that you like it. So similarly our cost function is now very authentic, it's verified from the principle of maximum likelihood. So that's a good thing. So I hope you understood. If you have any doubts, please write in the comment box, and please share this video and subscribe to this channel. Bye bye.